Welcome back, folks. We are embarking on the home stretch of this course. Today we're going to look at solving systems of equations. And today will just be two variables that we're solving for, two equations, two variables. Next recording is going to get really exciting. We'll have three equations, three unknowns. That'll be really fun. And then we have other excitement in store following that too. But for today, systems of equations. All right. So first we'll look at linear systems. These are a system of equations is when you have more than one equation and you're trying to figure out what the common solution is for those equations, for that 2, 3, 4, however many equations you have. And we're first going to look at linear systems where all of the equations are equations of lines, hence linear. And so in your case, you're going to have two equations, both will be equations of lines, and you're trying to figure out what ordered pairs or what points work in both equations at the same time. What's the common solution? So we're going to look at several techniques for figuring this out. Now, as you solve and get your solutions, you have a couple of different possibilities. You could end up with one solution. In this case, the system of equations is said to be consistent because there is a solution. And then there's one solution, so the two equations, the graphs, intersect in one point. The equations are said to be independent because they are two separate lines. They're not coinciding with each other. And so you get the two lines, they intersect in one point, one coordinate pair, and that ordered pair where they intersect is the solution to the system. Another possibility is that you could end up with no solution. This is an inconsistent system. If there's solutions, it's considered to be a consistent system. If there's no solution, it's considered to be inconsistent. And in this case, your equations are independent because the graphs of the lines are two separate, distinct lines. Independent, they're distinct lines. Dependent, they're coinciding lines. So independent, they're two separate lines, but they don't intersect each other. They run parallel to each other. So then there's no solution. And then you could also have infinite solutions. So we're back to having answers, which makes it a consistent system. But in this case, the lines are coinciding. So it makes this dependent equations. One line's right on top of the other. They're essentially the same line in the same location on your graph. And all the solutions are found on that line because all those ordered pairs on that line are in common between the two equations. So when you go to express your solution, you end up just re-expressing the equation on the line. In your book, there's going to be a very specific way to do that, and I'll show you when we get there. Okay, so three methods for solving. We're going to look at examples of each method. Substitution, elimination. Those two are both analytical methods, where you're working it out with pencil and paper, and then graphing, where you graph them and see where the intersections are. You can do that with pencil and paper, or you can do it with a graphing calculator, depending on what you're allowed at that point. So we're going to look at substitution first. We're going to look at the two analytical methods first, and then we'll go back and use the examples to also look at the graphing method. Substitution is exactly what it sounds like. You're going to take one of the equations and solve for one of the variables and use that to substitute into the other equation. Starting out, the problems are complicated in that there's two unknowns to solve for. So in both analytical methods, both substitution and elimination, the goal is to get it down to a single equation with one variable, one unknown. So when you make your substitution in the substitution method, you're going to end up with that one equation, one variable. You're going to solve. That'll give you one of the variables, and then you'll plug that back into one of the full equations and solve for the other variable. And then when you go back and check, substitute your ordered pair into each of the original equations before you started messing with anything, and make sure the ordered pair works in each one. Because in order to be a solution to the system, it can't just work in one equation, it has to work in both. And then if you're solving and you get stuck, let's say you're solving and suddenly your variable completely disappears on you, doesn't necessarily mean you've done anything wrong. If you have no variable, but you're left with a true statement, you've got infinite solutions. That's the coinciding lines. If you're left with no variable and you have a false statement, that's the no solution or parallel line situation. So getting an answer is the intersecting in one point situation. So, and again, I'll show you examples of some of those as we go along. All right, so let's look at our first example for using substitution to solve. Let's take 2x plus y equals negative 11. That's our first equation, linear equation. If you graph this, you'll have a line. And let's take x plus 3y equals negative 8. And let's figure out what ordered pair will work in both of these equations at the same time. All right, now for substitution, pick one of the equations and solve for one of the variables. In this case, there's two easy ones. You could take 2x plus y equals negative 11 and you could solve for y. Or you could take x plus 3y equals negative 8 and solve for x. Either one of those would be easy to solve for those variables, so take your pick. I'm going to take 2x plus y equals negative 11. I'm going to put a little box kind of around these to show that's the original question. All right, I'm going to take 2x plus y equals negative 11. And I'm going to solve for y by subtracting 2x from both sides. And now I have an expression for y. I have negative 2x minus 11. So then I could take x plus 3y equals negative 8, and I can make a substitution for y. I can take this negative 2x minus 11, and I can plug it into this equation for y. Everything else in this equation is going to stay the same. Just in place of y, I'm going to put parentheses, negative 2x minus 11. And that's my substitution. Okay, now that I've made my substitution, I've got one equation here with one variable, x. I'm going to go ahead and proceed to solve for x. So distribute your 3, combine like terms, add 33 to both sides, divide by negative 5 on both sides. All right, so that's one of your variables. You get x equals negative 5. Now you're not quite done yet. You got to solve for y too. But from earlier, you know that y equals negative 2x minus 11. So you can do negative 2 times negative 5 minus 11 and see what you get. 10 minus 11, and you get negative 1. So your solution is ordered pair negative 5 comma negative 1. There's your solution. And if you want to check, this ordered pair should work in both equations. So go back to your original equations, go back to 2x plus y equals negative 11, plug in negative 5 for x and negative 1 for y. You got negative 10 plus negative 1, and that is negative 11. So that works. Then also go to x plus 3y equals negative 8. Plug in negative 5 for x. Plug in negative 1 for y. You get negative 5 plus negative 3, which is negative 8. So that worked as well. Woohoo! So my check shows that that ordered pair does indeed work in both equations. So when I graph, later I'm going to graph these two, not yet, I'm going to do a little bit later, but when I do, you're going to find that those two equations are lines that intersect at this point, at negative 5 comma negative 1. All right. Let's do another example here. Let's do -3 plus -3x plus 2y equals -10. And we got 9x minus 6y equals 30. I don't see like an easy peasy one to pick, but you know, it doesn't really matter. You can pick either equation, either variable. I'm going to take -3x plus 2y equals -10, and I'm going to go ahead and solve for y. So I'm going to go ahead and add 3x to both sides and divide by 2 on both sides. Okay, and I'm going to take this and plug it into the equation 9x minus 6y equals 30. I'm going to take 3x minus 10 over 2, and I'm going to substitute it right here for y. Okay, let's see what happens. Let's see, 6 and 2 reduce right here down to 3. So really I have a 3 to distribute. Minus 3 times 3x is minus 9x. Minus 3 times minus 10 is plus 30. Uh-oh. 9x minus 9x is 0. So I end up with 30 equals 30, which is a true statement, but no x. So in this case, I've got the coinciding lines. I've got infinite solutions. Okay. So in order to express the solution, there's a couple ways you can do it, but let's go with how your book does it. One way to do this would be to go ahead and write an ordered pair and just let x be the generic x. So you're saying, you know, whatever x is, you know, it goes there. And then the y, we said earlier, y equals 3x minus 10 over 2. So we can go ahead and put that in for the y value, 3x minus 10 over 2. So then people know that you can pick any real number you want for x and put it here, and then 3 times that minus 10 over 2 will give you your y. And that's the way you can generate your ordered pairs. So you have infinite solutions, but they're all ordered pairs that fit this pattern right here. So it has to be x comma 3x minus 10 over 2. Let me erase that little mark I just accidentally made. There we go. Okay, so that's how you're going to express things for the infinite solution situation. When we graph it later, you're going to see that the two lines are right on top of each other and that the ordered pairs all fit this pattern. Okay, second analytical method, elimination. This one sounds like something on a game show or something. Elimination round. Okay. Again, analytical method, the goal is to get it down to one equation, one unknown. Way easier to deal with. So we're going to choose one of the variables we want to eliminate. I mean, if you have a grudge against x, pick x. If you have a grudge against y, pick y. I don't care. Pick one of them. And then you're going to get it set up so that the coefficients, the numbers in front of that variable you chose, are opposites. When I say opposites, you know, opposites are things like 2 and -2, 8 and -8, 1/3 and -1/3. You know, a number and it's negative. So we're going to set it up so the coefficients are opposites. And we can do that by multiplying each equation by some constant other than some number, real number other than 0. And then we're going to add the two equations together, the two new equations we get. We're going to add them together. And when we do that, we're going to end up with one equation, one unknown. And we're going to solve it. Take the solution, substitute into one of the full equations to find the other variable, and there you go. There's your ordered pair. And again, check by substituting the ordered pair into both of the original equations. All right, so elimination method. Let's look at this example first. We got 5x plus 7y equals 6. And we got 10x minus 3y equals 46. You can pick either a variable, but in this case, I think x is going to be the easiest to get rid of, because in front of x here you have a 5, and in front of x there you have a 10. Well, you could take the first equation and multiply it by -2, and that would give you a negative 10x and a positive 10x. So then you have your opposites you need. If you really like x and don't want to get rid of y instead, I mean, you could do that. You would have to multiply maybe this first equation by 3 to get 21y, second equation by 7 to get the negative 21y. So, you'd have to multiply both equations by something. It's up to you. All right, let's take 5x plus 7y equals 6, and let's multiply by -2. So that we get negative 10x minus 14y equals negative 12. Entire equation is multiplied by that -2. And we're going to take that and add it with 10x minus 3y equals 46. Going to add those two together. So we got negative 17y equals 34. So y equals -2. All right, then I'm going to go back to one of the equations. It doesn't matter which one. I'm going to choose 5x plus 7y equals 6. I'm going to plug in that -2 for y. So I got 5x minus 14 equals 6. 5x equals 20. X equals 4. So now I've got my ordered pair solution. 4, -2. And that ordered pair works in both equations. Go back to the 5x plus 7y equals 6. Plug in the 4. Plug in the -2. I've got 20 minus 14, which is indeed 6. And then go back to the 10x minus 3y equals 46. Plug in the 4. Plug in the -2. I've got 40 plus 6 equals 46. And that's true too. So it checks out. But that's your elimination. Okay, let me do one more of those. 3x plus 2y equals 5. 6x plus 4y equals 8. Okay, it doesn't really matter which variable I get rid of. Let's say I get rid of y. Well, I can take that first equation and multiply by -2. So that I get -6x minus 4y equals -10. And I can add that with the second equation, 6x plus 4y equals 8. Add those together. Well, -6x plus 6x is 0. -4y plus 4y is also 0. -10 plus 8 is -2. Those are not equal to each other. So this is false. This is not true. So there's no solution. This is a situation where if you graph those two lines, they're going to run parallel to each other. They're not going to intersect each other. And in your book, you're going to see that they use the null set symbol. to show no solution. The solution set is empty. And I got kind of carried away drawing my null set symbol, so let me redo that there for you. Like you guys are listening, you're fine, but if you go back and look at the notes later, you'll be like, what is that? So it looks like a 0 with the slash through it. That is not 0, that's something called the null set or empty set. And there's nothing to check because there's no solution. But there you go. All right, let's explore graphing with some of these examples we just did. You can graph one of the equations in y1 and the other in y2 and use intersect in the calc menu to find where the two cross, if they do. Sometimes the window needs to be adjusted to see any intersections. Okay, let's revisit 2x plus y equals negative 11. And x plus 3y equals negative 8. In order to put these in the calculator, you have to solve each one for y. Because remember, in the calculator graphing section, it's y1 equals, y2 equals, etc. So you got to make sure you solve each one for y first. Okay, and then you can use those two forms to put them into the calculator. So let's see here. Y equals, I'm going to be putting in negative 2x minus 11. And then for y2, I'm going to put negative x minus 8 divided by 3. And then hit graph. Okay, so I see the two lines. Y1 was this line, Y2 was that line. I can go to second trace, which is the calc menu, and I can use number 5 to compute the intersection of the two lines. My cursor right now is where? Looks like it's on the line going down too far, so let's go this way. What? I'll show you where my cursor is. Gotta find it. There it is. Right now the cursor's on that line, so that's my first line, first curve. Enter. Then it jumped to the other line. That's the second line or second curve. Enter. And yes, guess where they intersect. Thank you very much. And you get negative 5 comma negative 1. And that's exactly what I expected, because when I solved this earlier by substitution, that was the solution I got for the system. Negative 5 comma negative 1. So there's an example of them intersecting in one point. Let's see, let's look at some of the others. Negative 3x plus 2y equals negative 10. We did that one earlier. That was the one with the infinite solutions. I just want to show you what these look like on the graphs. And we had 9x minus 6y equals 30. Okay, so first equation, we're solving for y. So we'll go ahead and add 3x to both sides. And then we'll divide by 2 on both sides. Second equation, we're going to subtract 9x from both sides. Divide by negative 6 on both sides. You could reduce that, but I'm not going to bother. But hey, if you do reduce it, you'll notice something. If you divide everything through by negative 3, if you factor out negative 3 on the top and bottom and reduce, you'll get 3x minus 10 over 2. And before you even graph it, you'll see, hey, they're the same. And that tells you they're coinciding lines. But just for the sake of graphing, let's kind of make it look like they're different, and let's put these two into the calculator. Okay, 3x minus 10 divided by 2. And then for the other one, negative 9x plus 30 divided by negative 6. And in order to really see this, let me go over here to the far left and change the thickness of y2. So I just, once that's over here blinking, I'll just hit enter once, and that'll make y2 a thick line. That way when we hit graph, you'll see y1 get drawn as a thin line, and then you'll see y2 get drawn as the thick line. Watch carefully, don't blink. Here we go, there's the thin line, there's y1. Here we go, there's the thick line, there's y2. They are right on top of each other, they're the same line. So that's why I did the thick, so you could see the thick line drawn right over the thin line. So that was that infinite solutions case, and that's why basically you're expressing the answer as the equation of the line, because the solutions are, you pick any x you want, plug it into the equation, and get your y, and that's a solution. Those ordered pairs are your solutions. Okay, one more of those. So I want to show you that infinite solutions scenario. Or I mean the no solution scenario, sorry. We just did the infinite solution scenario. The no solution scenario, we had 3x plus 2y equals 5. And we had 6x plus 4y equals 8. All right, solve for y. This one I'm going to subtract 3x from both sides. Divide by 2. This one I'm going to subtract 6x from both sides. Divide by 4. If I go ahead and factor out a 2 in the numerator and denominator and reduce, I get this. Two lines with the same slope, but notice that the y-intercepts are going to be different. This one's going to have a y-intercept at 5/2 or 2.5. This one's going to have a y-intercept at 2. So that, same slope means same slope, but different y-intercepts means they're going to be parallel to each other. Excuse me. But let's go ahead and graph them anyways and play with that. All right, clearing it up. Negative 3x plus 5 divided by 2. And then the next one, negative 3x plus 4 divided by 2. Or heck, if you don't believe me, we can do negative 6x plus 8 divided by 4. And then hit graph. And you'll see them running parallel to each other. Kind of hard to see like this, but we can zoom in. Over to enter. But yeah, they're running parallel to each other. They will never touch. So there you go. That's the no solution situation. Little null set symbol. Okay, and all these examples so far are linear systems where the equations are lines. The same techniques can be applied to nonlinear systems. In other words, equations where the graphs aren't lines. You've dealt with them already. I mean, you've graphed parabolas, you've graphed the rational functions, quadratic functions with parabolas, you've graphed the rational functions, you've graphed all kinds of stuff. So nonlinear systems, same techniques, but just not necessarily dealing with lines. So I'm going to do 2 examples of those. All right, first example, I've got x minus y equals 3, which actually is a line. That's okay. And I've got x squared plus y squared equals 9. which that's actually a circle, which we haven't learned about yet, but you will in a few more lessons. The last lesson we're going to do will involve circles, and that's my favorite lesson in this course. I love doing it. All right, I'm going to use substitution. You could use elimination if you want. A little bit difficult with this one, but not impossible. But I think substitution's way easier here because I can take x minus y equals 3, and I can easily solve for x by adding y to both sides. And then I can make a substitution into x squared plus y squared equals 9. I can take this y plus 3 and substitute it in for x. I got y plus 3 squared plus y squared equals 9. Okay, y plus 3 quantity squared. Y plus 3 times y plus 3 gives me y squared plus 6y plus 9. Then I got plus y squared equals 9. I can subtract 9 from both sides. I got 2y squared plus 6y equals 0. Factor out 2, factor out y, and then you got y plus 3. So y equals 0, y plus 3 equals 0. So y equals -3. You actually end up with two y values here, which means you're going to have to go back and find the x values that go with each of them, and you're going to have to, might have two or more ordered pairs for your solutions. Okay, you just found y equals 0, y equals -3. Well, go back to x minus y equals 3. You can use that one. Plug in 0. You get x is 3. So 3 comma 0 is one of your solutions. Go back to x minus y equals 3. Plug in -3 for y. And you get x is 0. So 0 comma -3 is another solution. So in this situation, you've actually got two ordered pair solutions. If you check it, you already know that they work in x minus y equals 3 because you just use that equation to find them. But go back to x squared plus y squared equals 9. 3 squared plus 0 squared does equal 9. And 0 squared plus -3 squared equals 9. And just for kicks and grins, you can still go back to here, x minus y equals 3. 3 minus 0 does equal 3. And 0 minus -3 does equal 3. So these check out rather nicely. And we're not going to get too much into the graphing yet because you guys have not covered circles. But I'm just going to quickly sketch this out. X squared plus y squared equals 9 is a circle of radius 3 with the center situated at the origin here. So forgive my rough drawing. But you've got this circle. And then x minus y equals 3. Well, that's equation of a line. Y equals x minus 3. So you got 0, -3, up 1 over 1, up 1 over 1, up 1 over 1. So you got this line that goes like this. So the points of intersection with the circle are at 0, -3, and at 3, 0. So that's your two ordered pair solutions there. That's your two common points between those two equations. So there you go. There's a nonlinear system using substitution, and this is what's happening graphically. All right, one more nonlinear system. Let's do one with elimination. I chose elimination for this one because it's really already set up for me. They have a negative y squared in this equation and a positive y squared in that equation. So when you add them together, your y's will go away in the elimination process. Of course, you come back later and figure out what y is, but for now, it goes away. Okay, so take x squared minus y squared equals 1. I don't even have to multiply the equations by anything because the coefficients in front of y squared are already opposites. Add these together. You'll have 2x squared equals 6. So x squared equals 3. So I feel like I did something wrong here. Oh, I miscopied the question. I did do something wrong. I apologize. Yeah, for that problem, you're going to get square root of 3, square root of plus or minus square root of 3. Why not? I'll just keep doing that one. I was using one in the book, and I was like, why is this not working out? But that's all right. We'll just keep doing this one. So x equals plus or minus square root of 3. So you get 2x values there. If you go back to either equation, let's say you go back to x squared minus y squared equals 1. Square root of 3 squared minus y squared is 1. So you got 3 minus y squared is 1. Negative y squared equals negative 2. Y squared is 2. So y is plus or minus square root of 2. So you've got square root of 3, comma, square root of 2. You've also got square root of 3, comma, negative square root of 2. So already got 2 solutions there. Then if you plug into that same equation and use negative square root of 3, well, it turns out you're just going to be back in the same business. So you're done. That's all that's going to happen with that. So then you just have 2 solutions. So however these two look when they intersect, they're only going to intersect in 2 points, and it's going to be these 2 points. All right. And you can check that if you want. You know, square 3, you get square root of 3 squared is 3, square root of 2 squared is 2. So as soon as you do that, you're going to have 3. Oh, I'm sorry, there actually are 4 points. Because you have to be able to take negative square root of 3 in there too. So over here, you're going to have negative square root of 3. I didn't write it down. Sorry about that. Comma square root of 2, and you also have negative square root of 3, comma negative square root of 2. Ta-da! So 4 ordered pairs total. Sorry. You square root of 3, whether it's positive or negative, you're going to get 3. Square the square root of 2, whether it's positive or negative, you're going to get 2. 3 minus 2 here is 1. 3 plus 2 here is 5. So all of them are going to work out rather well in those equations. X squared plus y squared equals 5 is a circle. And then x squared minus y squared equals 1 is going to intersect that circle in 4 places. All right, I'm going to do one more example with you guys. Your homework involves a couple of word problems. Not very many, but a couple. So I want to do a word problem example with you. And that is on page 422 in your current textbook, number 80. So the box has an open top, rectangular sides, and a square base. The volume of the box is 576 cubic inches, and the surface area of the outside of the box is 336 square inches. Find the dimensions of the box. All right, so they tell us about the shape and they tell us the volume and surface area. Not very helpful otherwise. And they want us to find the dimensions. All right, so let's do it. So they're telling us we have this box, open top, so we don't have to worry about the top. But we do have to worry about the fact the bottom is a square. And I'm going to go ahead and draw this flattened out. Like if I took the box, cut the corners, and just flattened it out, this is going to be the bottom. And then the sides, since there's no, just cut perfectly, sides are going to look like this when it's flattened out. Each of those is a side. It's 4 sides. All right. It says the volume of this box is 576 cubic inches. It says that the surface area is 336 square inches. And we have to use this information to figure out what's going on with this box. Now the bottom is a square, so let's go ahead and just use X for the side of the square. And then the height, we don't know what it is, let's use a Y for that. Let's use Y for the height. Okay, so volume of a box is length times width times height. So in this case, we've got 576 equals X times Y. So 576 equals X squared Y. And then surface area, you got to add up the areas of all the surfaces. Okay, so you can add all those areas up. So this 336, see the area of the bottom is a square, X times X is X squared, plus this side is X times Y, this side is X times Y, this side is X times Y, and that side is X times Y. So we have 4 sides that are XY. So there we go. Let's use this. Substitution or elimination. Not sure elimination is going to work so well because I have an X squared Y here and an X squared plus 4XY here. So I think substitution might be my better bet. Let's see here. They are talking, everything's in cubic inches. Just thinking for a second about what I want to have. I think I'm going to go ahead and solve for this one for Y. And then I'm going to make a substitution over here for Y. So we got 336 equals X squared plus X and X squared, you'll reduce. So 4,304 over X. And then you try and solve for X. Do I want to do that, or do I just want to put this in the calculator and see what happens? If it doesn't tell you how to do it analytically, you can always put this in the calculator and see what you get. That's sounding a little more entertaining right now. Let's try that. Start solving something. If you're not really caring for the way you're doing it, you can always try something else. How about we take this one, rewrite it in terms of Y. All right, I'm going to put those into the calculator and see where they intersect each other. All right, so y sub 1, we're putting in 576 divided by x squared. And then y sub 2, we're putting in the numerator 336 minus x squared. And then denominator, we're putting in 4x. These got some crazy numbers here, so I don't think it's going to appear right on this little grid. I think I'm going to have to zoom out some. I should zoom out probably quite a bit. Times 3, zoom out. Okay, I'm not seeing it yet. Okay, zoom out. Interesting. Excuse me. I'm curious. Zoom out further, see what it looks like. Yeah. Okay, so it's kind of weird shape. So let's zoom back in. Really not, since it's the sides of a box, I'm really not interested in negative numbers. I can just eliminate that possibility over there. I don't need that. You know, since when does a box ever have negative sides, right? So I'm just worried about over here on the right side, positive x values. So let's calculate intersection. Whoops, sorry, I hit the wrong thing, didn't I? There we go. Need new glasses. All right, where is my cursor right now? There we go. Okay, we want that curve. We'll hit enter. And then where's my cursor? Is it on the other curve? That's what I'm trying to figure out. Not sure. Well, it should be on there, so let's go ahead and hit guess. That's a lovely decimal, isn't it? Ay, ay, ay. So much fun dealing with these crazy decimals. All right, it's looking like it's trying to work with stuff that's a little too close to the axis here. So let's try computing this again. Let's do second calc, number 5. Where's my cursor? It's tricky trying to get it to put things in the right places, right? Let's do this. Let's hit enter, guess. All right, this graph, it's not giving me the results that I need. So maybe I need to rethink this. Sometimes you get frustrations. Well, we'll go back to playing with this and then look at the graph again. Let's see here. Earlier I said, well, I didn't feel like dealing with the rational equation, but it looks like I might have to. Oh, well. Let's see. This one, multiply through by x if I want. So it doesn't make sense to have a cubic to worry about, does it? It might be easier to graph that instead of trying to graph this dang other thing. Yes, I said dang. Sometimes you get these frustrations, you gotta work through them. I can't figure out why it's giving me something so crazy on those other two. All right, let's try that. Let's try x cubed minus 336x plus 2304. Let's see what that gets us. This time I want to compute my zeros here. So let's do this. Let's do window from 0 to 40, scale of tens. Max 0 to 40, scale of 10. Let's see what that gives me. All right, it gives me those two parts. So let me go back, change my window a tiny bit. Let's try y min being 10. Oh, not 10, sorry. Y min, let's try it being negative 10. Because I want to figure out the zeros here, like where this thing crosses the x-axis. So let's calculate 0. Can't find my cursor. Oops. Why don't I see my cursor yet? Go too fast. There it is. Don't blink, you'll miss it. All right, that's left bound, enter. And then you go down and you get right bound, and then enter. Okay, so 9.1. That makes more sense. All right, so 9.10 for that one. So there's two x values. For whatever reason, that other graph just was too much to handle. But here we got 9.1. And then calculate the other 0, number 2, left bound. Let's get it down and hit enter. And let's keep going. Get it back up. Did I miss it again? Go too fast, you miss it. There it is. It's up again up there. Hit enter, enter. And we get 12. Yay! That makes a lot more sense. All right. So you know what? Since we ended up using this one, yeah, just ignore this. We ended up graphing this one. Getting the zeros. We got x equals 9.1 for one of them, or 9.10, and we got x equals 12 for the other. This is all in inches. But we got to find y. Well, plug into the equation up here, 576 over x squared, and you can get your y. And you would end up with y is 4 inches for this one. And you could end up with 6.96 inches for this one. and that'll get you your y. There you go. So the box has two possible dimensions. It could have a base of 9.1 inches and a height of 6.96 inches, or it could have a base of 12 inches and a height of 4 inches. All right, well, there you go. So thank you for joining me and for being with me as we worked through that word problem. You have plenty of those to practice, and when you tune in again, we're going to have fun with 3 equations and 3 unknowns. See you soon.